Hello and welcome to our sixth in the series of customer webinars. Today's webinar is on large power transformer design, manufacturing and testing considerations. I am Rajiv Kumar and I'm the Director of Marketing for Virginia Transformer. With me is Parminder Panesar, the Technical Director for Virginia Transformer, and Balakrishnan Mani, who is the Research and Development Supervisor for Virginia Transformer. Bala and Parminder will be taking us through this webinar.
Let's start.
Well, hello and welcome to the sixth in the series of our customer webinars. And these webinars are being conducted as part of our 50th anniversary celebrations this year. And thank you for your participation. The topic for today's webinar is large power transformer design, manufacturing and testing considerations for generator step-up and auto transformer large power transformers. My name is Rajiv Kumar. I'm the Director of Marketing for Virginia Transformer. With me is Parminder Panesar, who is the Technical Director for Virginia Transformer, and Balakrishnan Mani, who is the R&D Engineering Supervisor. So Parminder and Bala will take us through the key design and manufacturing and testing considerations for these extra large power transformers. There will be CEU credits associated with this webinar, which will be provided post the webinar upon sending a request to the marketing ID. This webinar is being recorded and it will be available on our website. And this will also go on YouTube as well, where it will be available for future viewing. If you have any issues in getting a link to the webinar recording, you can always reach out to the marketing email ID in the invite, and we will link you up accordingly. I now invite Parminder Panesar to give an overview of how these extra large power transformers integrate into a power system network.
Thank you, Rajiv. Thanks for the introduction. And so we're going to get started how these transformers, power transformers, large power transformers, auto generator transformers, these are all running our power system as of today. So the slide which you see, it gives a basic one-line diagram and specifically concentrating on the transformers, where they're placed, what kind of purpose they serve. So on the top left-hand corner, you see a generator which is generating power at somewhere between 5 kV to 25 kV, which is most common voltage for these generators. So next comes GSU, generator step-up transformer, and that will step up the voltage from the generating voltage, which could be 25 kV, to transmitting voltage, which could be 230, 138 kV, 345 kV, up to 500 kV for the US systems, and some other countries have higher voltages. So one difference for GSU is the ratio is very high. It is picking up the voltage at a low voltage, which is generated by at the station, and at very high current, and steps up the voltage, reduces the current to the transmission level. In some of the cases, there is another step up transformer which is being utilized. So step up happens not in one single step, but 2 steps. And that second transformer could be auto. So if first GSU did up to 138 kV, next auto transformer could step up from 138 to 230 kV or 345 kV. So now that is a step up function which happened as close physically possible to generating station to reduce losses. Now, at the distribution place where the power is being utilized, we'll have various step-down transformers. Depending on the ratio, customers may opt for going into auto transformers. They do have some benefits. We'll go through those in details in the slides. So, but at various load utilization places, depending on the utility of power, a customer would have different type of transformer, rectifier duties, if it's industrial based on their load, motor starting. So those kind of things would be used, and they are generally small transformers. The biggest pieces which we are looking here are on the top line for stepping up.
Okay, I now invite Balakrishnan Mani to take us through the key design considerations, the standards to be followed for this extra large power transformer design.
Thank you, Rajiv. First is the standards which are applicable to any transformer. Starting with, we have a general standard C571200, which everybody follows, which outlines the general requirements, temperature rises and other requirements, and test requirements in this. And we have C571210, which normally covers the standard requirement in terms of accessories and DETC, LTC, all other requirement and the settings required for the transformer to operate. And we have test standard, which is C571290. This covers almost all type of transformers and for liquid type. And this has the connections and the time and the configurations for different types of transformers. When it comes to the loading, C5791 is used for all type of transformers which are filled with mineral oil. And there is no standard specifically for an auto transformer. However, the GSU transformer has a standard which covers the requirements and the power system design considerations to be considered for GSU. And the standard is C57116, and this is applicable to transformers directly connected to generators. And there are two other standards which covers smaller GSUs for, say, solar application, and there is one more that is not listed because we are going to talk about a large GSUs in this presentation.
So, Bala, now take us through, what constitutes a generator step-up transformer. Sometimes, some transformers that are large but perform a function like the collector transformers for solar and wind installations are confused with generator step-up. So what really is a generator step-up transformer? Can you take us through that, please?
Right. So the generator step-up transformer, or GSU, or sometimes called as unit transformer, they are directly connected to a generator or generator bus, and normally have LV voltage of, say, between 5 to 25 kV, and steps up to a transmission level voltage. And the speciality here is, since it has a connected to generator bus, and the bus arrangement can have breaker or no breaker, and it depends on the application, and the ratio between HV and LV will make it complex. And also the system voltage changes, something called as load rejection. All these things makes this transformer is different from a collector transformer. And what is a collector transformer? Collector transformer is a transformer which is connecting smaller GSUs, say solar GSU. We will have many small GSU which will be together connected to a large transformer, and that is normally called as a collector transformer, and some people still call it a GSU. And the design consideration wise, the collector transformer is different than a GSU, and GSU requires additional considerations in terms of core design and core overfluxing. And the guide which we saw in the previous slide, C57116, lays out the differences and the operating conditions for GSU, and we shall see those in the upcoming slides.
Thanks, Bala. Now let's talk a little bit about the large autotransformers.
So large autotransformers by itself, autotransformer is special because of the winding construction and winding connection. And you see on the illustration on the right, the part of the winding, low voltage winding, is actually part of the high voltage winding. And this gives certain advantages and some disadvantages when it comes to design. But overall, this is economical for an interconnecting transformer, and this economy depends on the ratio between the high voltage and the low voltage winding. Say, for example, if we have an auto transformer rating 138 by 69 kV, so your auto ratio is 0.5, and if you have 138 by 34.5, then the auto ratio is slightly higher because you have a bigger difference. And we shall see how this is advantageous in the next slide. So what is the real advantage when it comes to the material content and other properties for an auto transformer with respect to the two winding transformer? So copper weight for an auto transformer depends on the auto factor or the core ratio, and there's a formula given here. From this we can estimate how much approximately this will be better or saving with respect to a standard transformer. And because we have lower amount of material, the losses incurred are less. So your copper is less, so you will have less amount of core, which gives us higher efficiency. And also the size reduces, and since the size of the core goes down, you have a lower excitation current. And the last point about the voltage regulation, this is special because in an auto transformer, you have both conductive and inductive transfer. So part of the high voltage winding is actually part of common winding or LV winding. So your impedance is actually lower impedance or magnetic leakage between one winding to the other winding. So you will have a better voltage regulation for an auto transformer.
So Bala is now going to take us through some of the detailed design considerations for these large transformers, both auto and GSU.
So starting with the design and the winding arrangement, for an auto transformer, we normally have an additional winding, tertiary winding, because this is an YY transformer. To suppress the third harmonic in the line, we always have tertiary winding. With that, starting with the basic configuration where you don't have a load tap changer, you will see the location of the winding with respect to the core. The first will be the tertiary, and then the common winding, and then the series winding. So common winding is actually a low voltage winding, and series winding is a high voltage winding. This is a basic configuration. And the next one is when you have a regulation. So regulation comes in between the tertiary and the common winding. So when some cases you want to add a regulation in such a way that you have some complexity with respect to the voltage, transient voltage. In some cases, we do use a regulation in between common winding and the series winding. And this condition comes along with an additional challenge, which is the joints in the regulation winding can cause higher heating because the main leakage happens between common and the series winding. And the last case is when you have regulation on the neutral side, so we can put the regulation as an outermost winding after the series winding. This is normally done in the industry. So for a GSU, it is very simple. The GSU will have mostly only two winding, low voltage and high voltage winding, and low voltage is of course an inside winding, and the HV is an outer winding. If in some cases, rarely, if you have an LTC or a regulation requirement, your regulation is an innermost winding, and normally the offload taps are in the body of the high voltage winding, and this is a typical condition winding arrangement for large GSUs. When it comes to the core construction, if it is a single phase, there are two options. One is three-legged core construction, and next is two-legged. And for a three-legged, the legs outside may have lesser area. It varies, depends based on the manufacturers. Normally they have 50%, right? 50%. And when it comes to three-phase, it is standard. We have three-legged construction. And when there is the size of the transformer is very high, or we are meeting with the limit of shipping, normally it is converted into a five-legged core with the outermost legs will have reduced area. And this construction is very rare, and it will be on the range of 300 plus MVAs. This construction is preferred. So winding wise, the construction is of three types. For a regulation winding in the large transformers, it is mostly a multi-start winding, and some people call it a fully distributed winding because your turns are distributed through the height of the winding. So this type of construction is actually advantageous over a olden method like a barrel type of winding you take by brazing in the leads, and this is advantageous in terms of short circuit requirement. And we can use CTC and a regular PICC for this construction. And next is the helical winding. Helical winding, as we know, this is a simple winding. You take bunch of conductor and winding with certain helix angle based on the turns and the height and everything. And the conductors can be CTC and PICC, but most likely 90+% it is CTC because large transformers, it is very difficult to meet the number of strands and the area required for the current. And the last one is the disc winding. This is mainly for the high voltage winding where you will have sometimes shields, which we call it a floating shield for improving the capacitance, series capacitance during the transient testing. And in rare cases, this can be a CTC if it is a really large transformer. Otherwise, it will be a regular paper insulated conductor. Most important thing about large transformer core design is optimum selection of the core duct and the core material. Since core is a big part of the core and coil assembly, the core flux and the core heat generated can be very high, and the requirement from C571200, which states that the core shall be designed for worst case scenario and meet the temperature limit of 130 degrees Celsius. And this 130 degrees Celsius is the hottest spot gradient in the core. And on the surface, the temperature may be less, and but there are some instances where customers comes back with certain limits, say 120 or 125 for larger transformers. In those cases, the optimum selection of cooling ducts and the location of those ducts becomes critical. So accurate prediction is possible, and it is okay to use two-dimensional FEA for core to arrive at the actual heating. And normally companies and industry has their own calculations which are validated by test by direct measurement. So with that, we can optimize and design the core to meet the IEEE requirement. GSU has a special requirement in terms of overexcitation. So what is this overexcitation? In the power system, we have something called load rejection. And when load rejection happens, the generating stations will see suddenly there is a loss of load, and your over voltage can increase up to 140%. And this may not be long time, but this is actually a power frequency over voltage, so it puts a lot of stress and increased flux in the core. And then next, when you have operating under lower voltage tab, and suddenly your system voltage increases by power system effects like Ferranti or any effect, you will see increased voltage which will be continuous. In those instances, the transformer core, especially the GSUs, has to be designed to meet overexcitation for a long period of time. Generally, customers expect or customer writes in their specification to have 110% continuous over voltage. And C57116 says at least we need to have to that level. And the graph here shows a typical example where you design for a certain flux density, which is in yellow. You have usual overfluxing. The overfluxing is in blue. It decreases and based on the time, and there is a saturation limit. So for a brief moment of time, it can operate in the saturation region, but not high. So normally, transformer designs for generator step-up application is designed close to or less than 1.65. And if there is additional requirement of power factor requirement, everything, then this can be more, further reduced to meet this requirement. So we saw about the winding and the core construction and some phenomena of core design. Now we will go into the next level, is the leakage flux losses and temperatures in the transformer. So based on the construction, what we shown on the rightmost, you have primary and secondary winding, and you have a tie plate, and the clamps together holds the core and coil, and then we have a tank. So the typical leakage flux pattern is shown here. So leakage flux is mostly axial, but it starts bending when it comes close to the ends of the winding, both at the top and at the bottom. So as the transformer size goes up, 150, 200, 250 MVA, your amount of leakage flux is increasing. And with that, your leakage flux density created by this leakage phenomena will be high in the winding, in the structural components, tank wall, clamps, and the tie plate, and which further leads to additional losses and additional loss density, which is most important comparing to a small or distribution or small power transformers. Your loss density is higher. From the loss point of view, the eddy loss is directly proportional to square of the thickness. And you have the leakage flux B0, which is a peak leak flux density. For a conductor, if we choose a thicker conductor, then because of your square relation, you will see higher eddy losses in the winding. And with that, we need to select smaller conductor size. However, the short circuit requirements will make it the other way around, where you need to select the high strength conductor. So that's the reason it is 90%, it is always a CTC conductor for low voltage and tertiary winding, to keep the hotspot within limits of 80 degrees Celsius for a 65C winding rise. And one more thing is regulation winding. The regulation winding should be placed in a low field region, because the current in large transformers, especially if it is GSU or large autos, auto may not have high current, but still if it has high currents, then the location of regulation is important, since if there is a joint in the leakage flux region, then the heating can be very high. So winding design in terms of short circuit requirement, generally GSU, the high voltage side is Y, and the standard short circuit requirement coming from C571200 is actually good enough for GSUs. But the problem is for auxiliary transformers in the generating stations are critical for short circuit, but GSUs are not that critical. But because of the strength and the size, we use epoxy bonded CTCs to keep these losses low and high strength. In some cases, you may need a silver bearing rectangular conductor, and this is only case by case basis. If the area required is smaller, but the forces are higher in those instances. And for an auto transformer, the connection is YNA D11 or D1. D represents the tertiary winding. And if it is unloaded, then the short circuit forces has to be estimated for single line to ground fault from both sides of the winding. And short circuit forces should be evaluated for that condition, and design should be managed according to the highest forces. And even in this case, the CTC is mostly used, in some cases silver bearing copper. The stray losses for the large transformers are really a challenging part, because stray loss can make a transformer competitive or less competitive if you don't correctly estimate based on the configuration and the size. So stray loss are of two types. One is generated directly by leakage flux or leakage field, and this is applicable to both large GSUs and auto transformer. Generally, these losses are occurring in tie plate, bracket, and the tank wall. When it comes to high current field, This is applicable to GSUs. As we saw, GSU low voltage rating is between 5 to 25 kV. So your current is going to be really high, 5,000, 6,000, 7,000 amps. You will see huge amount of high current field in the lead exits regions, and where you have a bushing plate, where you have bushing taken out, and then even in the installation in the generating station where you have bus arrangement, and there also you will have a strong magnetic field generated by this current. And C57116 recommends to perform additional FEA to limit these temperature rises, and it also explains the utilities or who buys the transformer interact with the manufacturer to evaluate these with the construction what we are seeing in the field. And the limit, generally it is not specified in standard, but limit for metallic parts is normally 140 degrees Celsius under worst case. So for a large GSUs, the design has to be validated or simulated for those conditions. And the illustration on the right shows the coupled leakage field analysis for one of our transformers. It shows that the heating on the bracket and the tie plate. You see here, if you see, it is 93.38. So this is for a surrounding oil temperature of say around 55 degrees Celsius. So the delta is around 30 to 40 degrees Celsius. And this is the problem where we need to change to material or follow some loss reduction techniques, which we'll see in the next slide. Stray loss control is very important for the large power transformers, any type of transformer. But if it is large, this becomes really challenging for manufacturers to estimate the stray losses. And the stray loss for a steel plate, which is actually an eddy current loss, is kind of different for a conducting material and material whose skin depth is very small compared to the plate thickness. So the relation here shows it is related to the square of the magnetic field intensity HO, which is a peak value, and we have conductivity and the permeability of the material also comes into play. And A1 is a linearization coefficient. Normally what happens for a magnetic material, the relation is B is equal to mu times H. So we don't know what is the mu value because the generated field will be different for each transformer and each location based on the clearances and the magnetic leakage. So accurate prediction of this peak flux intensity, and test-based factor for A1 will give us the accurate loss in the type plates. And with that, we can determine whether we need to go for stainless steel or to go for a magnetic tank wall shunt. So what it does, the magnetic tank wall shunt will attract the flux and will not let the flux to go into the tank wall. And if it is a non-magnetic material, what happens is that the flux attraction is 0. So you won't get more flux attracted to the plate. So in that instances, your stainless steel will have lower losses, and approximately 40 to 50% compared to the mild steel or structural steel what is being used for transformer building. And shunts normally of CRGO but M6 material, that is good enough. And it is always advisable to go for edgewise shunt, and that's what many companies use, and that is advantageous over widthwise shunt, where your laminations on the front may get saturated. So these are all the techniques which is used to reduce stray losses. And what happens, this gives an advantages in terms of controlling the temperature on the tank wall, temperature on the tie plate, temperature on the bracket.
Thanks, Bala. Now I would like to invite Parminder to take us through some key manufacturing considerations for these extra large power transformers.
Thank you, Rajiv. Bala covered pretty good details about the design consideration, what are the important factors for these transformers when you go into large, high power, high current, high voltage consideration, and how calculations are done, how we verify that everything is meeting the IEEE as well as customer specifications. So, all is done in paper. Now it's time for us to put in practice and make sure the transformer quality is good. It's going to last for years to come, and serve customer the needs. So very important factor, which I'm going to start with this one, and we'll move into the other standard parts. And this is a bridge of manufacturing practices as well as the design requirements. High current joints. So for GSU, when the current goes in thousands of amps, it becomes more critical, very critical for us to ensure that these current carrying parts, all the joints are done properly. They carry current, and the joints have minimum contact resistance to cause any overheating in the service. So the common practices which manufacturers follow, and depending on what capabilities they have, they're bolted joints, brace joints, and crimp joints. So brazing is done. All the joints within the winding, they're all brace joints. Joints which come out of the winding winding wire out of the coil, when it connects to the flexible leads or the cables, they could be brace joints, or they could be crimp joints, most likely crimp joints. So each manufacturer has their own way of qualifying these processes, and these are all special processes, brace and crimp joints, and they verify, hey, the joint which we're going to follow this particular process, qualify our equipment, qualify the operators, certify them, and then once that is done, then put those things into practice. So it's a collaboration between engineering and manufacturing capabilities. So these are commonly used joints, but they hold very important role for any transformer which is going to last for years and carry very high current. So we covered the important aspect of current carrying joints. Now we're going to go through other processes which are important. They hold, they're becoming more important for large power transformers, and let's go through them one after other. So as we know, windings are heart of transformers. So life of transformer is pretty much life of insulation, which majority of insulation resides within the winding itself. And design has done their part to ensure the forces, the life, the temperature, the loss of life, all is as needed. Now, when it comes to manufacturing, we have to keep the tight tolerances, and those tolerances become more critical. And in these transformers where looking for large power GSUs and Autotransformers, so tolerances are tight. You can imagine the diameter of about 2 meters will have only tolerance of 3 millimeters or less. So, and similarly, the actual height will have tolerances. There are few reasons to do those tight tolerances, and first is to keep the actual parameters as close to the design parameters. Second thing is for the winding to have good short circuit strength, they need to be tight. They need to be tight within themselves as well as from one coil to other coil. and to observe these short circuit forces. Now that is the radial tightness of winding. When it comes to axial, the actual construction of these windings are, they have key spacers, they're actually clamped with a force which is equal and opposite to the short circuit forces. So in service, the transformer coils are clamped with those forces within the transformer body itself. And however, in the process, first to ensure that it is going to meet the actual height and the physical center of the actual heights of windings is not too different. Again, that has tolerance. The center line of the actual center line of the winding needs to be within certain millimeters. So that way, we don't increase the forces which will come under short circuit, the actual forces, I mean. So in order for us to do that, the winding has to be sized or calibrated to the right dimension as engineering is looking for. Again, very tight tolerances, 3 millimeter or less in the height of about almost 2 meter coil. And in order to achieve a stabilized height of these windings in process, we use isostatic. And the drying process, depending on the voltage class, could be simple air drying with vacuum, or it could be vapor phase drying, or it could be vapor phase drying plus oil spray to ensure the stabilized coils have reached. And it's very important at that point in the winding stage for us to stabilize the measure height accurately, because that is what the job is going to have once it goes into the tank, oil filled, and stays in service. So what we talked previously was the processing of winding, which again, as I said, we utilize VPD for large power transformers for first stabilizing and calibrating the winding sizes. So now from there, another important, which I would say the most important process of drying which happens is the complete coherent coil. And VPD is the process, vapor phase drying is the process which is utilized for such transformers, which gives us 0.5% moisture, because it's very important. There's so much literature available that achieving 0.5% moisture at the initial stage of manufacturing before transformer is first filled with oil is very important, because it relates to the overall life of transformer. So the way a vapor phase works is, the whole process of drying happens in vacuum chamber, and the media which is used for convection, for the heat transfer is vapors again. So the process happens under vacuum, under heat temperature, pretty much 110, 120, it can go up to 130 or 140 degrees Celsius. So it is an accelerated extraction of moisture. And this process can easily extract moisture up to 3-4 inches thick pre-compressed board, or high density pre-compressed board without any issue. So that is important to govern the last end parameters of this process, ensure that we have achieved 0.5% moisture. Now, once that is done, the transformer insulation has shrunk, and all these supports, the lead support which we have done, that needs to be retightened. So once it comes out of vapor phase drying, it has to go through the full clamping process of tightening all the leads, maybe retorquing of some of the electrical connections, also clamping the coils to the required force which is given by engineering. So all those that takes some time, and it is very important was to ensure that exposure time during that process is controlled. That work has to happen at wall footing basis without interrupting any work, and ensure, count the time when it comes out of vapor phase and when it goes in the tank under vacuum. So that time needs to be monitored and ensured that we meet our internal set criteria. So once it goes into the tank, lead is welded, or and then it has to go through vacuum process. The idea of putting vacuum which is about 1 torr or less, to extract any surface moisture which the insulation has absorbed during the work which we performed. So holding the vacuum, which could be 24 hours or longer based on the voltage class of transformer, is important. The second important thing which happens this time is the oil filling. But before we fill the transformer with oil or dielectric fluid, it becomes important for us to verify the oil has the right quality. Specifically, I think it's very common for any manufacturer, or it is common or should be done to measure the breakdown value as well as the moisture contents in oil. These are two very basic properties of oil which will determine if it is good or not. And these tests could be extended to other testing like IFT and power factor measurement of dissipation factor of oil. So those are the added tests, but I would call the breakdown voltage and the moisture content to be very basic, and ensure we are meeting the criteria as defined in IEEE. And from there, under vacuum, the transformers are filled with oil. And again, at that time, the rate is regulated to ensure the transformer insulation is getting enough impregnation of oil. The first filling of oil is very, very important. It's very important that each pore gets filled with oil, and it gets its required dielectric strength, which of course we want to test it when we perform the dielectric testing on the transformer. So when it comes to testing, IEEE as such does not differentiate any specific thing for GSUs or auto transformers. But by default, there are a few challenges which comes with the properties of these transformers. For instance, for dielectric testing impulse, GSU has low voltages, is a really up to 25 kV, and with the high capacitance, it could be challenged to get the reduced and full wave shapes for impulse. And of course, there are various parameters, permutation combinations available in the impulse generator itself to try to match the required wave shape and match the capacitance and get the required wave shape. And also IEEE allows there's some variation if you can't get to that point. There is possibility of using a tail resistor which is outside. So that actually is a challenge. Getting wave shape on HV may not be of any concern to LV. Otherwise, GSU testing is pretty much standard as a two-winding transformer. It might take longer time for temperaturized tests because the leads are heavy current, and the shorting for the LV becomes a challenge again. But as far as IEEE numbers, testing procedure, it does not differentiate. Now, when it comes to auto transformer, there are a few differences. Again, standard procedures are same, but when we talk about impulse for auto transformer, so in general, if you have HV, say a 230 kV HV, the impulse distribution is throughout from 230 to 0 volts. Whereas when we have 230 and 138 kV LV for an auto transformer, then the whole impulse distribution happens only between 230 terminal and 138. So your drop of voltage across the winding turns is much steeper than the normal transformer. So engineering watches that when they design it, and of course, that when we test it, there are few considerations which we have to see and ensure, and if they're using external resistors and the time resistors used to ensure that these terminals don't get higher voltages than they're rated for. So those are the precautions which are taken. Similarly, for auto transformer, the load losses calculations are different because while I explained in one of the slides, the current which flows within the winding is not simply kVA divided by the voltage class. It varies because of series and common winding. So the voltage, the current which flows through them is not straightforward. So we use the calculations to to get to the point what current flows through series and common winding, take the resistances, calculate the I square R, and the load losses are corrected accordingly. So another thing which becomes critical, not from testing point, but becomes part of manufacturing. If it is an auto transformer and has a LV line end LTC low tap changer, which for LV it will be line end. Say for instance, 230 kV HV and 138 kV LV. The line end LTC for LV will be 138 kV, which could be 550, 650 VIL. That become one of the critical process in manufacturing to ensure right clearances across the phases of LTC. So those are critical parameters, which of course they are critical during manufacturing, but again, to watch them, ensure that proper clearances are maintained, and then they will be successful in testing. So all these things, they make power transformers, large power transformers, as a special product. It is not, you can't simply extrapolate the process which we're using for 10 MVA, take it to 100 MVA, from 100 MVA to 300 MVA. There are a whole lot more considerations taken when we design and manufacture these transformers. So we covered, Bala and I tried to cover this in about 40 minutes time. In a brief, there's a whole lot which goes behind the scenes, calculations, verifications, and also ensure that our winding, our prints and drawings, they translate the right thing from design information into the shop, and things go flawlessly, seamlessly, and we end up in a product which passes all IEEE and customer requirements, and from there it goes to field and serves customer for years to come. So this is we try to cover. Any questions we are here to answer. Jenna, we have any questions?
We have one. Are all of these transformers considered power transformers?
So a power transformer, again, they're limited by the definitions of IEEE, but in general, the bigger GSUs, they are under power transformers. Auto transformer, in general, when it goes into power system, generally they are rated for 69 kV and above. There'll be also power transformers. So some GSUs, they are like pad mounts, which again, they are classified under pad mount, especially for renewable application for solar and wind. So they are covered under different classification of pad mounts. But I would say there are a few exceptions, but we are 90 to 95% correct in calling them all of them to power transformer. There are a few exceptions though. So,
okay, thanks everyone, and again, greatly appreciate the participation. A couple of notes here. Again, the webinar is being recorded and will be available on YouTube and on our website. If you need or if you have any questions on the link to the webinar, please email us at the marketing email ID provided in the invite for the webinar. Also, if you need CUU credits, continuing education credits, do email us at the marketing email ID, and we will supply the same.
And any follow-up questions, they can always send to the same
ID as well. You will get a follow-up email from marketing, which will list the contacts and where to pursue any additional information or questions you may have. Thank you again, and we will see you all in the next webinar. Thanks.